Friday afternoons. I can't see why it can't be more late. I'm sure it's somewhere.
So you've got homework 5 due tonight, cellular automata. Just to keep things rolling, I've got homework 6 posted now. That will be due. It's a weird due date. It's actually Tuesday after we get back. So because it doesn't really matter whether it's a class day or not, right? I mean, you can just submit it whenever, and it'll give us a chance to sort of get our minds right Monday after spring break and maybe answer some questions, and then you can hack away at it and turn it in Tuesday. Some readings there. On Monday, I'll add some more. We're essentially going to be going through chapters 10 and 11. So if you want to read ahead or what have you, 10 and 11 are what we're covering. And we're introducing the notion of classes, which are really probably the biggest innovation that C++ offers over, say, C, for example. And we'll talk about classes today. Emily will do her presentation. And then we'll finish with, we'll actually write a class, or at least start writing a class that will represent complex numbers. So we'll have a bit of a review about how complex numbers work, and then we'll write a class to actually represent complex numbers. Questions? Ever any questions? Oh, Rachel, yay.
So for the homework that's due tonight, or just in general, how much of the program is it reasonable to change from what your instructions say to be part of the above and beyond? Or if we're changing any part of it, would you just
I would say
submit that one and then create a second one to also see?
The safest thing would probably be to make a second one. But if you've got some above and beyond and it doesn't change sort of the fundamental specifications of the assignment, for example, you still have the range check from 0 to 255, you still have a default rule, it still has kind of maybe that initial condition or some initial condition that you're controlling, and I mean it's a judgment call, but if it's a significant change, it's probably easiest to just copy it and send me a different one. And put a comment at the top of the one that you feel like satisfies the assignment, telling me about this other above and beyond file. Other questions?
Wait, I do have a question.
Okay.
So for the while loop at the very beginning of the generate number function, so I'm having an issue with making it so after you've inputted an incorrect number and then prompted again, to still do the default if you just hit enter.
Right. So several people I've actually noticed had this, I guess I'll call it a bug or an oversight. You ask for a number, the user enters something that's out of range, like 300. Now you drop into a loop and you're trying to get a number that's in range. Mm-hmm. What you need to do is reset the default value. So the reason that you're in that error loop is because rule is at 300. Oh. When you go back in there, set rule back to 110, and then go through the process of continuing to ask. Gotcha. A lot of people forget to do that.
Cool.
Okay. All right, so today we introduce data abstraction. It's probably the most powerful feature of C++. I'm going to start by talking about a more primitive version of data abstraction or encapsulation that C actually introduced way back when Dennis Ritchie came up with it in the late 70s, called a struct, which is short for structure. And then I'll talk about what Strustrup added to the struct to make classes. He took the idea of a struct and extended it in C++ and gave us the notion of classes. So a structure A struct is essentially a new data type that is essentially composed of, I never know the difference between composed and comprised, but we'll use composed of sort of sub-variables, also called fields. Of existing data types. So lots of times you're a programmer and you're working with some kind of data that, in a sense, rightfully belongs grouped together. A good example of that would be like you have a program that has lots of dates in it. A good way to represent dates is using a struct. So, for example, dates. A date has 3 pieces of information associated with it: a day, a month, and a year. And instead of carting around 3 variables all the time to represent a single date, wouldn't it be better if we could somehow group these 3 variables, month, day, and year, into a single data type, say a date data type, and then we could just pass around these date variables all over the place, and then whenever we want the day, we reach inside and grab the day, or when we want the date, the year, we reach inside, grab the year, and so on. That's what these things get you. So let me give you some syntax. Let's continue this example, and let's do struct. Let's call it date, and that's an open curly brace. And then inside, what kind of data type would a day be? An int, yeah. And a month. Yeah, okay. I'm going to store it numerically, but I definitely take your point. It could be like February, the word February. I'm going to stick with int and then year. And there's a weird syntactical. There's a semicolon down here. Don't forget that. Don't forget that semicolon. All right, now I put this at the top. Above the first time I actually use one of these things. And then down in main, I can now declare things like dates. For example, I can go date, birthday. The advantage here is with this single declaration, I'm actually allocating 3 variables, or defining 3 variables. One for the day, one for the month, one for the year. And I can access those fields in the following way. So birth.day, say 2, birth.month, say 6, and birth.year, say, I'll use my wife's, 1968. Now, if I have a function that, say, print dates, I don't have to feed it 3 pieces of information. I can just feed it birth, print birth. And then it'll go in and grab those fields and print them however you like. So there's a period here. birth.day, birth.month, birth.year. And this is the member selection function. It's goes in and it grabs the correct member of the struct. Yes.
If you just said see out birth, or
it would fail.
But how would it print it out? Just like all the integers with no spaces?
It would just literally fail. It would say, I don't know how to print this out, and you get a compiler error.
Okay.
So we're going to talk a lot about that very question probably next week sometime. But right now, if I do something like see out birth, this will fail. This will be a compiler error. It'll say something like function cout doesn't know how to work with the date data type, something like that. Sarah.
Can you have different data types within?
Yes. So I could have a date up there, and then I could further. So right in here, I could do something like struct medical record. And then in here I could do something like date DOB, and then I could have other stuff too, and then close it off. So now I have a struct that has another struct inside of it. And you can regress this as far as you want. You can have structs within structs within structs. The only thing that you have to be careful of is that you define the date struct before you define the medical record struct. Questions about that? And then if you have a medical record, let's say I'm just sort of continuing on this. Maybe we have medical record and we'll just call it A. And let's say we want the month of the patient's date of birth. Then you would do something like this: A.dob.month. And that'll reach into A and grab the DOB field, and then reach into the DOB field and grab the month. Make sense? So yeah, you can have layer upon layer upon layer of these structs. You should be careful about how deep you want to go. It's rare to see, say, more than 3 deep. If you go more than 3 deep, then it gets pretty confusing. You can also make arrays of these things. So for example, I can do a date, call it D80. Oops, come on. So I could make an array of 80 dates, and I could go in and get the month out of, say, the third, out of date 3. And that will go into the fourth date and grab the month field out of that. So I can make arrays of these structures. So it's quite flexible once you define it. You can treat the struct just like any other data type. In most cases, you can assign one date to another date. So if I have, or one struct to another struct. Let's say we have date A and date B, and we put some stuff in A, then we can write B equals A, and this will copy contents of A into B. And at least using the tools that you have up to this point in the semester, that's a safe operation. When is it not safe? We probably won't do too much of this in this class, but C allows you to, while the program is running, it allows you to go out to memory and grab a chunk of memory and bring it into your program. Whenever you're doing stuff like that, then these assignments usually fail because it's not the assignment operator is not smart enough to figure out that you've got this extra memory attached. But don't worry about that for now. So it copies the contents of A into B. You could also have a struct with an array inside. And then down here you could have, say, data, record, and if you want to reach inside and get one of those array elements, you can do something like record dot a 3. Okay. Yeah. An interesting thing about structures is if I have two records, say record 1 and record 2, and let's change that to record 1, I can actually do things like this. And the array will actually copy correctly. It's really interesting because you can't copy arrays out in the main program. Like if you have array A and array B and they're both length 80 and you say A equals B, that's going to fail. But if you tuck them both inside of a struct, or if you tuck them inside a struct and then copy the structs from one to the other, it'll actually work. It's pretty bizarre. Questions about that? So a lot of this and other examples are in the book, section 10.1 about structs. This lets us encapsulate data. For example, let's say we want to build a print function. For the date struct. Well, we could do something like the declaration void print date. Right, so there's the declaration. It says I'm going to make a function called print. It has no return value and it takes one date argument. And then down below, I could define as follows, and I can just do something, print it out nicely, like cout. Let's see. I guess in this country we often do d dot month, and then maybe we'll put out a backslash or something like that, and then d dot day. And then maybe another backslash, and then d dot year, and we'll be done. And this will print out this date object in a sensible way, month slash day slash year. If you're writing a print function for date objects that maybe is going to be used in an international context, you could actually provide another argument, date format. Maybe DD, MM, YYYY, and you can have other kinds of format strings that you might dump in as a second argument. And then this print function gets more complicated. It would have like a selection of different possibilities depending on the format that you chose. Maybe you have a European format, or you have, what have you, different ways of printing things out. What's nice about this, again, though, is instead of carrying around these 3 variables and always kind of working with these 3 variables, the print function just takes one argument, D. And then it goes in and does the right thing. It pulls out the data that it needs, prints it out in the format that you need. But in general, it's a little bit cleaner to group these pieces of data together in a single data type. Questions? M? Yay? Go ahead.
Yeah.
Say when, M.
Okay, hang on. It's loading. No. Okay. So I'm presenting with a Raspberry Pi, which the idea of this is basically it's a little programmable computer for kids. And so there's a group of people started in the UK who noticed that the skill level of computer science applicants for programs was declining. They felt like in the 1990s kids came in as hobby programmers into the program, whereas in the 2000s maybe they've run a web page, maybe they've worked with graphics a little bit, but it wasn't enough for them to really be successful in the program. So what they wanted to do was create a small, cheap, programmable computer that would hopefully allow more kids to have access. So they created the Raspberry Pi Foundation, and it is a nonprofit foundation. They wanted to give kids a way to have a computer to program, because so much emphasis nowadays is on teaching kids to use Excel or use Word, but not teaching them how you can word process, how the computer word processes, how you can program your computer. So with the relative inexpensiveness of mobile device processors, they said, okay, we'll use that and create a small computer using an SD memory card as its form of memory. And they created 2 models. They geared, in their mind, Model A more towards the educational sector, therefore not needing internet, and Model B more towards home use, so that kids could have a computer at home and not have to worry about tanking mom and dad's work laptop or the home computer. So the basics of it is it supports HDMI. You can connect it to any analog or digital TV, and you can add a keyboard or potentially a mouse if you have Model B, and it's powered by a micro USB. And this is what it looks like. It's about that big, so just a little bit bigger than the size of an Altoids tin, and you can see based on the size of the SD memory card next to it. This here is the Model B. So for the price of $25 for Model A or $35 for Model B, kids can, in a monitor that you could probably procure from Goodwill, kids can have a computer that they can program. So what can it really do? Graphics-wise, they say it has the capacity of like an Xbox One, but its real capacity, like in terms of performance, is a Pentium 2 processor, so like a Pentium 2 but with much swankier graphics. Its default programming language is Python. Operating system-wise, it runs a couple different versions of Linux. It will not run Ubuntu due to their newer updates, and it does have audio support. So the big idea here is that it's a computing revolution for kids, that they can have a computer that their parents can afford, that they can program, and hopefully build up those skills before they apply to the different college programs or whatnot. It is a new and evolving project. When I picked this question, I went onto the website, raspberrypi.org, and they didn't even have a picture of it. It wasn't even in production yet. But now when I'm giving this today, they're producing it, and Google has gone out and bought up thousands of these and is donating them to schools across the UK. So I encourage you to check it out. It's a really cool, interesting, developing program, and I think it's a really great idea to build kids' skills in these areas and not just focus so much on Word or Excel and the computer as a calculator, but what you can get the computer to do.
Questions?
Tony.
What power does it run on? Do you use it like?
It has a micro USB plug into it, and then you just plug it into an outlet.
So you use it with a monitor?
Yeah, you just it's just a regular monitor, and it plugs in like into the side of the video. Yeah.
Or 3. Yes.
There you go.
I think that yellow.
The yellow, yeah. So.
I'm trying to identify. You can see the USB ports on the bottom left there. There's 2 of them.
Mhm.
Looks like audio, maybe?
Yeah.
One is audio.
Let me go to the website, and they explain what everything is. Let's exit. Let's see if we can find the graphic. There we go. So the one we were looking at was rotated, but that's the explanation of what it is.
Oh, I see. It has analog video out and HDMI.
Mhm.
Cool. Ethernet upper right, USB. Doesn't have a case.
It does not have a case.
So you gotta be careful.
And you gotta be careful, and people are like, oh, will it fit in an Altoids tin? And they said no, because they don't round the corners of their board off. If they did, it would fit in an Altoids tin, but yeah, it doesn't have a
I'm
case.
concerned about all the pins.
No kidding, right?
Coming out of the bottom and shorting out on the Altoids tin. So
Yeah.
I might go with just build a little wooden box. Or
Box.
a cardboard box or something. Yeah. There's a kid in the art department. I can't remember his name. Yeah, thank you. Who is taking one of these and doing an art project with this and an old scanner. I think his plan is to scan 4 miles of the railway that runs through here and out into the country. And then I don't know what he's going to do with it. But I'm looking forward to that in the senior exhibit as well. Other questions? Rachel?
Where did you get the name?
I don't know. Let's see.
Yeah, you would think that would be a...
It's just, I don't remember reading where it got the name. And let's, about. I don't know.
question.
It's a good
I'm sure it's
question,
in there
though.
somewhere.
Yeah, it's probably in there somewhere.
All right.
Yeah.
Thanks, Em. Raspberry Pi. Okay. Let me, everybody's using Prezi now. I feel so old-fashioned. All right. So, back to structures and classes. A structure was something that was available in the C programming language, and it was a way of abstracting data so that you could take related pieces of data, related variables, and group them together in a meaningful way. For example, month, day, year, group them together in a date structure. This was all well and good, and it certainly was quite useful. Strustrip, though, when he came along and built C++, said, it's not all about the data. It's also about what you do with the data, right? So there's the data, and then there are the things that you usually do to that data. Things like, for example, we've talked about strings in here a little bit, right? Let's talk a little bit more about strings, and you'll perhaps get an idea of perhaps get an idea of what I mean by grouping not only data together, but grouping data and related functions together under one data type. So that's what a class attempts to do. So the AND functions part is what Strustrup added to structs to get classes. The one example, actually there are several examples of classes and and variables that are classes that you've run into, but probably the clearest cut version would be the string class. What data? First of all, let's back up. What's a string? Remind me what a string is in computer science. It's an array of characters. So what's the data that's associated with a string? The character array, right? So if I were going to make a string struct, what would the field be? An array of characters, perhaps? Yeah. So I'll do something like character A80. I keep picking on 80, but now there's a severe limitation here when I make a string struct like this and I let the data be A80. What's the limitation? I can't have more than 80 characters in my string. And there's a few other things that this primitive structure leaves us wanting. Strings can be lots of different lengths. So even if we stay within the 80 character limit, you could have a string that has 2 letters in it, a string that has 20 letters in it, a phrase that has 35 characters in it. And it might be useful for us to know exactly how long the string is. So if I have a phrase that's, say, 35 characters long, it doesn't consume the entire character array, right? So it's going to go from 0 up to 34, and then from 35 out to 79, there's nothing there. And if I decide to grow the string at some point, I've got space, but there's no real way of knowing how big the string is. So I might add a field to this guy. That has the size, and I might say, well, every time I add a character to this string, I'm also going to make sure that I set size to the appropriate size. So if I have a 35 character string in there, I'll make sure that I make size also 35. That way, this guy carries around information not only about what the data is, but how many characters there are, because that seems to be a common thing to want to know when you're working with strings. So we could do that. Let me go back and let's go back to this example here. Okay. So here I'm using the string class, and I declare a string, and I get the string from the user, and right down here, see this guy right here? length is a function that is often related to strings. It's something that we care about with regard to strings. So what strustrip allows one to do is to not only have the data that represents the string, but to have functions. See this little dot operator? What did that do with structs? What was that for when we were using structs? Yeah, it goes in there and grabs the field, right? The particular field. And that field was data. The extension that strustrip added is now this guy can go in there and get a function out of the variable. That's weird. So it'll reach in there and grab the length function and call it. And what this guy will do, what does this guy do? It tells me how many characters are in that particular string. Not just general strings, but this string right here. And there are literally dozens of different member functions in the string class. Let me show you what I'm talking about. So there's the data of the string class, the actual characters and perhaps the number of characters. Here's the documentation for the string class. There's a lot of gobbledygook here, but if you go down a little bit, you'll see there's the length function. This returns the length of the string. There's also a size function that does precisely the same thing. Here's a clear function. What do you think that does? It empties the string and does one other thing. You may not really be thinking about this yet, but it's going to set the size, right? So there's this piece of data in there that keeps track of how many characters in the string. It's going to set that back down to 0. If you go up here, you can actually see the data that's in there. Yeah, this is a little bit more technical than I would like, but the data here is attached to this guy. It's a character pointer, and I thought there was a size. Yes, there's a size right there. So there's some other data in there that I'm not going to explain, but the two important pieces of data are this guy, which is essentially the character array, and this guy, which is the current number of characters in the string. And then you have these member functions. But there's other stuff. When I write a class, there are lots of features that I can put on the class. This guy, for example, this operator with the square brackets, this gets a particular character of the string. So that's considered a function that's associated with the string. There are a couple of others here. I can get the last character in the string and the first character in the string. I can append a character to a string, either with the plus equals operator or with an actual call, dot append. This is also append. I can insert a character at a particular location in the string. I can remove characters from particular locations, replace, I can swap, lots of different things I can do. It gets even more. I can search the string. I can convert the string into what's called a C-style string. I can find the location of a particular substring. I can find the first occurrence, the last occurrence, lots of stuff. I can substitute. Sorry, not substitute. I can extract a substring. Let's look at that guy. So this will return a newly constructed string object with its value initialized to a copy of a substring of this object. And the arguments are, where should I start grabbing the substring, say character 4, and how many characters should I grab? 8. So I'll start here and I'll grab 8 characters. I'll take that out and turn it into a string. Right, that's also a member function. Did you have? Oh, okay. All right. So what we want to be able to do in this class is build our own classes. I don't know why, I kind of have an idea of why, but we don't call, let's go back to this guy. So when we have a variable that's of type string, and then somewhere down here we declare a string, this is called an object. It's a string object. This is the name of the class, and this is an object in that class. So that's the nomenclature that we're going to use here. And we're going to be writing classes, and then when we declare a variable in a particular class, that's called an object of the class. And that's where the word object-oriented programming comes from. If you look at the textbook, there's lots of discussion about objects and object-oriented programming. That's all it is. That's the nomenclature. So somebody writes a class, say string, and then you declare objects in that class. And the objects in the class have data and functions buried inside them. All right, let's talk a little bit about writing a class. So today we're going to put some math into Ma167, and I'm going to talk about complex numbers. Didn't we do a little bit of this with the quadratic function thing? Yeah, okay, so we've kind of already seen this. A complex number is really a pair of real numbers. A is the real part and B is the imaginary part. Yes. So we call a complex number Z A plus IB if the real part of Z is A and the imaginary part of Z is B. This has a nice geometric representation. Let's just call it the complex plane. So we can build something called the complex plane, where the x-axis, or the thing that we normally think of as the x-axis, is the real part, and the y-axis, the vertical axis, is the imaginary part. And every complex number has a representation in this plane. As just an ordered pair, AB. You go out a distance A on the real axis, and you go up a distance B on the y-axis, and or on the imaginary axis, and that tells you where your complex number is. And there's a whole algebra of complex numbers. For example, I can add two complex numbers. Let's say we have two complex numbers, Z and W, A plus IB and C plus ID. To add them together, you just add the real parts and the imaginary parts, and you're done. So Z plus W is just A plus C plus I times B plus D. And that gives you a new complex number, presumably. Subtraction is similar. Multiplication's a little dicier. So we have these two complex numbers that we want to multiply together, and we use the FOIL method. First, outer, inner, last. So we'll multiply the first guys, A times C, then the outer guys, then the inner guys, and then the last guys. ID. First, outer, inner, last. And just to keep with the form, the standard form of a complex number, what I'm going to do is group these guys together so that I can see what the real part and see what the imaginary part is. This is clearly a real number. These two guys are clearly imaginary numbers. This guy out here turns into what? Does anybody know? Negative b times d. Because you have I times b times d. And what's I times I? Negative 1. That's the definition of I, the square root of negative 1. So you take the square root of negative 1 times the square root of negative 1, and you get negative 1. And that's what's weird about complex numbers or imaginary numbers. In the real world, that doesn't happen, but in complex numbers, it's perfectly fine. So I'm going to group these guys, AC minus BD, there's the real part, plus I times AD plus BC.
Is there a plus in between the I and
Yeah, other than
Yes, thank you. Now, this is not how you would guess that two complex numbers would be multiplied together. Maybe you would guess, just AC plus IBD or something like that. That's just not, this is how we do it. So this is the multiplication formula. The division formula is even scarier. Well, I guess we can talk a little bit about it. Yeah, I'll have to talk about complex conjugation. So there's this thing called the complex conjugate, which is the complex number that you get by changing the sign on the imaginary part. And this is a little bar up above, and it means complex conjugate. A nice thing about the complex conjugate is if you take z times z bar, using the multiplication that we've already defined, you get a lovely result. A squared plus b squared. We can actually take advantage of that fact to define division. So let's look at z divided by w. What I'm going to do is write that as z divided by w times w conjugate over w conjugate. W conjugate over w conjugate is just 1. And what I've done is I've reduced this division problem into two smaller problems that I understand. 1 over w times w bar, this guy here, that is a real number. Right? And this is just some complex number, which I can figure out from up here. And then all I need to do is know how to multiply a complex number by a real number. So if I have a real number, say alpha, and I want to multiply it by z, that's the same as alpha a plus I alpha b. So z times w bar Looks like that, right? That I can do. I can just multiply it out. So let's do, we get AC. That's the first. Let's do the outer. Let's do the inner. And let's do the last. That's going to work out to be BD. Let's group these guys together. That's AC plus BD plus I times BC minus AD, like that. And this is just a real number, so that's AC plus BD over C squared plus D squared plus I times BC minus AD over C squared plus D squared, and that is the division formula. It's pretty scary. Now, why am I presenting this as an example of classes? We'll do one last point and then I'll let you go. What's the data for a complex number? Okay, be more specific. Yeah, two doubles, right? The real part and the imaginary part. So you would write a class and call it complex, open curly brace, and the private part of this class is going to be two doubles, which I'll call real and imaginary. That will just go. And then the public part will be all the associated functions, and we'll talk about this on Monday. And we'll talk about what public and private means. Until then, have a good weekend. Oh, forgot my semicolon again.
Yes. All right. So about that question I was referencing earlier.